Experimental probabilities are based on the results of actual experiments and adequate recordings of the happening of the events. These probabilities are only estimates. For example, if we toss coin for another 1000 times, we may get different data giving different probability estimates. As the number of tosses of the coin increased, the experimental probability of getting a head or tail came closer and closer to 1/2. The 18th century French naturalist Comte de Buffon tossed a coin 4040 times and got 2048 heads. The experimental probability of getting a head in this case was 2048 upon 4040, that is 0.507. J. E. Kerridge from Britain recorded 5067 heads in 10,000 tosses of a coin. The experimental probability of getting a head in this case was 5067 upon 10,000 equal to 0.5067. Statistician Carl Pearson spent some more time making 24,000 tosses of a coin. He got 12,012 heads, and thus the experimental probability of a head obtained by him was 0.5005. We can notice that as the number of tosses increases, the experimental probability of a head or a tail seems to be getting down around the number 0.5, that is 1/2, which is what we call the theoretical probability of getting a head or getting a tail. At the end of this chapter, you will be able to solve simple problems based on theoretical, also called classical, probability of an event.
Terms in probability. Random experiments. In random experiment, all possible results are known in advance, but none of them can be predicted with certainty. For example, if a coin is tossed, we can't say whether head or tail will appear. So, it is a random experiment. Outcomes. The result of a random experiment are called outcomes. Tossing of a coin is a random experiment, and it has two possible outcomes, head or tail. Equally likely outcomes. Events are said to be equally likely if we have no reason to believe that one is more likely to occur than the other. For example, when a die is thrown, all the 6 faces 1, 2, 3, 4, 5, 6 are equally likely to come up. Sample space. The set of all possible outcomes of a random experiment is called the sample space. It is denoted by S, O, omega, and its number of elements in the set is denoted by Ns. The element of the sample space are called sample point or event point. For example, in throwing a die, the number that appears at top is any one of 1, 2, 3, 4, 5, 6. So here, S is equal to 1, 2, 3, 4, 5, 6 and Ns is equal to 6. Similarly, in the case of tossing of coin, S is equal to head, tail or HT and Ns is equal to 2. Examples of random experiment and their sample space. Tossing of a coin, S is equal to head, H, tail, T. Ns is equal to 2. Tossing of 2 coins, S is equal to HH, HT, TH, TT. Ns is equal to 4. Tossing of 3 coins, S is equal to HHH, HHT, HTH, HTT, THH, THT, TTH, TTT. Ns is equal to 8. Drawing a card from pack of cards having number from 1 to 10. S is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. NS is equal to 10. Throwing of a die, S is equal to 1, 2, 3, 4, 5, 6. NS is equal to 6. Throwing of two dice, S is equal to 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2. 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 4. 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 5. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. NS is equal to 36. Playing of cards back. 26 red cards, 26 black cards, 13 heart cards, 13 diamond cards, 13 club cards, 13 spade cards. 4 suit, diamond, heart, club, spade. Denominations 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, J, Q, K. Card having number 1 is called ace cards. Face cards, 4 kings, 4 queens, 4 jays, 12 face cards. Event. Every subset of a sample space is called an event. Events are generally denoted by capital letters A, B, C, except S. For example, in throwing a dice, sample S is equal to 1, 2, 3, 4, 5, 6. Let A be the event of appearance of an event number A is equal to 2, 4, 6. Clearly, A is a subset of S. Also, N A is equal to 3 and N S is equal to 6. Always, N A is greater than is equal to NS. Types of events. The event which contains all the sample points of sample space is called a certain event. Let S be a sample space. If E is a subset of S and is equal to S, then E is called a certain event. For example, if dice is thrown, S is equal to 1, 2, 3, 4, 5, 6. Let E is equal to event of getting a number less than 7. E is equal to 1, 2, 3, 4, 5, 6. So, E is a certain event. So, we can say in a sure event, NE is equal to NS. Impossible or null event. An event that does not contain any sample point of sample space is called impossible event or null event. For example, A is an event of getting a number greater than 8 when a die is thrown. S is equal to 1, 2, 3, 4, 5, 6 and A is equal to 0. Null. A is impossible event, NA is equal to 0. Elementary event. An event consisting of only one sample point of a sample space is called an elementary event. For example, a die is thrown. Let A be the event of getting a score on the surface which is divisible by 5. Here S is equal to 1, 2, 3, 4, 5, 6 and A is equal to 5. Event A is an elementary event. Compound or mixed event. A subset of the sample space which has more than one element is called a mixed event. For example, in throwing a dice, the event of appearing of odd numbers is a compound event. For example, E is equal to 1, 3, 5, which has 3 elements. Complement of an event. Let A be an event of sample space, the set of all outcomes which are in S but not in A is called complement of event A and is denoted as A or AC. Here A occurs if and only if A doesn't occur. Also, A union A dash is equal to S. A and A dash are complementary events of each other. Mutually exclusive or disjoint event. Let S be the sample space and A and B be two events of S. Events A and B are said to be mutually exclusive if they do not have any sample point in common. That is, A intersection B is equal to phi, then A and B are mutually exclusive events. When a coin is tossed, the event of occurrence of a tail are mutually exclusive events. Exhaustive events. Two or more events are said to be exhaustive events if their union is a sample space. For example, a die is thrown. Let A be the event of getting number less than 5 and B the event of getting number greater than 2. S is equal to 1, 2, 3, 4, 5, 6. A is equal to 1, 2, 3, 4. B is equal to 3, 4, 5, 6. AB is equal to 1, 2, 3, 4, 5, 6. AB is equal to S. Events A and B are exhaustive events. Hence, if A, B is equal to S, then A and B are called exhaustive events. Note, if A intersection B is equal to phi, then A and B are mutually exclusive events. If A union B is equal to S, then A and B are exhaustive events. If A intersection B is equal to phi, and if A union B is equal to S, then A and B are complementary events. Complementary events are both mutually exclusive and exhaustive events. Hence, A union A dash is equal to phi and A union A dash is equal to probability of an event. Probability of an event A of a finite sample space S is written as PA and is measured as PA is equal to number of sample points in event A upon number of sample points in S. PA is equal to NA upon NS. Properties of probability. P phi is equal to 0 and PS is equal to 1. That is, probability of an impossible event is 0 and probability of a certain event is 1. Proof. P phi is equal to N phi upon Ns is equal to 0 upon Ns is equal to 0. PS is equal to Ns upon Ns is equal to 1. So, probability of an impossible event is 0 and probability of a certain event is 1. If S is the finite sample space and A is an event of S, then 0 is greater than PA is greater than 1. Proof. As A subset S, phi subset A subset S, NA is less than or equal to NS. N phi less than or equal to NA less than or equal to NS. 0 less than or equal to NA less than or equal to NS. Dividing the inequality by NS, we get 0 upon NS less than is equal to NA upon NS less than is equal to NS upon NS. 0 less than is equal to PA less than is equal to 1. Thus, probability of any event lies between 0 and 1, both inclusive. If S is the finite sample space and A is an event of S, PA dash is equal to 1 minus PA, where A is the complement of event A. Proof. We know that A union A dash is equal to S and A intersection A dash is equal to phi. N A union A dash is equal to NS and N A intersection A dash is equal to 0. NA plus NA dash minus NA intersection A dash is equal to NS. NA dash is equal to NS minus NA. Dividing both sides by NS, we get NA upon NS is equal to NS upon NS is equal to NA upon NS. PA dash is equal to 1 minus PA. Probability is always represented as fraction. Probability of any event always lies somewhere between 0 and 1. Note, PA union B is equal to PA plus PB, then A and B are mutually exclusive events. PA plus PB is equal to 1, then A and B are mutually exclusive and exhaustive events. They are complementary events. B is equal to A dash.
Example 1. Find the probability of getting a head when a coin is tossed once. Also, find the probability of getting a tail. Solution. In the experiment of tossing a coin once, the number of possible outcomes is 2. Head, H, and tail, T. Let E be the event getting a head. The number of outcomes favorable to E, that is of getting a head, is 1. Therefore, PE is equal to P head is equal to number of outcomes favorable to E upon number of all possible outcomes, equal to 1 by 2. Similarly, if F is the event getting a tail, then PF is equal to P tail equal to 1 by 2. Example 2. A bag contains a red ball, a blue ball, and a yellow ball, all the balls being of the same size. Kritika takes out a ball from the bag without looking into it. What is the probability that she takes out the 1. Yellow ball, 2. Red ball, 3. Blue ball? Solution. Kritika takes out a ball from the bag without looking into it. So, it is equally likely that she takes out any one of them. Let Y be the event the ball taken out is yellow, B be the event the ball taken out is blue, and R be the event the ball taken out is red. Now, the number of possible outcomes is equal to 3. The number of outcomes favorable to the event Y is equal to 1. So, PY is equal to 1 by 3. Similarly, PR is equal to 1 by 3 and PB is equal to 1 by 3. Note 1. An event having only one outcome of the experiment is called an elementary event. In example 1, both the events E and F are elementary events. Similarly, in example 2, all the three events Y, B, and R are elementary events. 2. In example 1, we note that PE plus PF is equal to 1. In example 2, we note that PY plus PR plus PB is equal to 1. Observe that the sum of the probabilities of all the elementary events of an experiment is 1. Let's solve some examples. Suppose we throw a dice once. 1. What is the probability of getting a number greater than 4? 2. What is the probability of getting a number less than or equal to 4? Solution 1. Here, let A be the event getting a number greater than 4. The number of possible outcomes is 6, 1, 2, 3, 4, 5, and 6. And the outcomes favorable to E are 5 and 6. Therefore, the number of outcomes favorable to E is 2. So, PE is equal to P into number greater than 4, equal to 2 by 6, equal to 1 by 3. 2. Let f be the event getting a number less than or equal to 4. Number of possible outcomes is equal to 6. Outcomes favorable to the event f are 1, 2, 3, 4. So, the number of outcomes favorable to f is 4. Therefore, Pf is equal to 4 by 6 equal to 2 by 3. Findings. 1. The events E and F in the example are not elementary events because the event E has 2 outcomes and the event F has 4 outcomes. 2. From example 1, we note that PE plus PF is equal to 1 by 2 plus 1 by 2 equal to 1, where E is the event getting a head and F is the event getting a tail. From 1 and 2 of example 3, we also get PE plus PF equal to 1 by 3 plus 2 by 3 equal to 1, where E is the event getting a number greater than 4 and F is the event getting a number less than or equal to 4. Getting a number not greater than 4 is same as getting a number less than or equal to 4 and vice versa. In 1 and 2 above, F is same as not E. We denote the event not E by E naught. So, PE plus P naught E is equal to 1. That is PE plus P naught E equal to 1, which gives us P naught E equal to 1 minus PE. In general, it is true that for an event E, P naught E equal to 1 minus PE. The event E representing not E is called the complement of the event E. We also say that E and not E are complementary events. Answer 1. We know that there are only 6 possible outcomes in a single throw of a die are 1, 2, 3, 4, 5 and 6. Since no phase of the die is marked 8, so there is no outcome favorable to 8. That is, the number of such outcomes is 0. In other words, getting 8 in a single throw of a die is impossible. So P getting 8 is equal to 0 by 6 equal to 0. That is, the probability of an event which is impossible to occur is 0. Such an event is called an impossible event. Answer 2. Since every face of a die is marked with a number less than 7, it is sure that we will always get a number less than 7 when it is thrown once. So the number of favorable outcomes is the same as the number of all possible outcomes, which is 6. Therefore, PE is equal to P getting a number less than 7 is equal to 6 by 6 equal to 1. So the probability of an event which is sure or certain to occur is 1. Such an event is called a sure event or a certain event. Note: from the definition of the probability PE, we see that the numerator, number of outcomes favorable to the event E, is always less than or equal to the denominator, the number of all possible outcomes. Therefore, 0 is less than or equal to PE is less than or equal to 1.